Alrighty, hello everyone. In this chapter, or in this lecture really, we're going to focus on two terms, solutions and molarity. So let's consider the beaker shown on the top right here. Okay, so what it's showing us is sodium chloride, NaCl. And if you recall, we had said previously that sodium is a metal, that chlorine is a non-metal, right, which we can identify based on their position in the periodic table. Sodium is in group 1A and chlorine is in group 7A. And we said that what they form is what we refer to as an ionic bond, right? It's an ionic bond, right? And metals are cations, whereas the non-metal is an anion, and the net charge of sodium chloride is 0. Well, in this particular case, we have sodium chloride in water, right? So what we have right here is basically water, right? So when we dissolve sodium chloride in water, we have what we refer to as a solution, right? So solution is basically a solute that is dissolved in the solvent, and water in this case is the solvent, right? And we'll define both terms solute and solvent in a minute. So how can we actually quantify the amount of solute present in the solvent? And that's when we're going to learn about the concept or the term molarity, all right? And we'll see in a minute that it's the moles of solute dissolved in the volume of solvents, right? The total volume of the solution, right? So it'll have units of moles per liter, all right? So what are we going to learn about? We're going to learn about three terms: molarity, right, which has the symbol capital uppercase M, which really has units of grams per mole. Which has units of moles per liter. We just said that. Has units of moles of solute per liter of solution. And from there, we're also going to take a look at moles, the volume of solution, which is what the liter here is describing. So if you're given molarity, moles, or volume of solution, you should be able to determine the variable. Notice molarity has units of moles per liter, right? Moles of solute over liters of solution. So if you have molarity and moles, you could identify the volume in liters. If you have the volume and the molarity, you could identify the moles of solute. If you have the moles of solute and the volume of the solution, you could determine the overall molarity, right? And we're also going to take a look at what if we have a concentrated solution and we wish to make it into a less concentrated solution. That's when we're going to learn about dilutions or dilutions, all right? Making a given solution less concentrated. You know, you could think of that similar to the solution that we just looked at, right? Suppose you have sodium chloride in water, right? And you fill up a given beaker halfway. But then suppose you go in and you add more water, and you only add water and not sodium chloride. So you just add more water. We're adding more of the solvent, and that's what we refer to as the solution being diluted. Typically, what we do is we add more solvent. All right, so let's take a look. All right, so we could describe solutions as something that is a homogeneous mixture, right? It looks like a uniform solution. In other words, if you put table salt in water, and you mix it and you take a look at the cup of water or salt and water, you won't really be able to tell that you have two different components, that you have the salt and the water. Similarly, if you dissolve sugar in water and you let it sit and you take a look at it, you won't be able to really tell that you have sugar in water unless you taste either, you know, the salted water or the water that has the sugar in it. Okay, so we call those solutions or homogeneous mixture, right? And what causes, you know, table salt to dissolve in water and sugar to dissolve in water versus if you put oil in water, they won't mix? Well, that has to do with a different concept that we'll discuss later called intermolecular forces, right? The homogeneous mixtures like table salt and water, for instance. Okay, so how can we identify the difference? What is the solute and what is the solvent? Well, the solute is basically placed inside the solvent, all right? And the solute will change its state. So in the case of table salt, it was originally solid, right? And then the solid dissolved in water. Well, which of the two components do we define as the solvent? Well, the solvent typically keeps its state. Like in the case of water, it's liquid water, it's still liquid water. But it's also whatever we have well, we're going to take a look at it, but the solute changes its state, right? So anything that's dissolved in water, we refer to that as an aqueous solution. So the symbol AQ meaning dissolved in water, all right? S is for solid, L is for liquid, G is for gas, but when something is dissolved in water, we say AQ, right? We're going to see that when we take a look at chemical reactions as well, right? If both components are liquid, if we're dissolving two miscible liquids, and which one do we refer to as the solute and which one do we refer to as the solvent? Well, whatever we have the largest volume of would typically be referred to as the solvent, right? So we said that we could describe a solution in terms of molarity, or the amount of solute in moles that's really dissolved in a specific amount, in a specific volume, right, of solution in liters. So molarity has the units moles per liter, right? And it has the symbol capital or uppercase M, right? Lowercase m refers to something else. So it's important to keep those units with the correct, you know, if it's uppercase or lowercase, right? And MOL is basically the abbreviation of moles, MOL. So it's moles per liter, that's molarity. And it's identifying where the concentration of the solution can be expressed in terms of the moles of solute dissolved in liters of solvent, or the liters of solution that we have. So what does it mean if we have a more concentrated versus a less concentrated solution? Well, it's the amount of solutes that are occupying a specific volume, right? Because it's the moles of solute per liter of solution. How many solutes are occupying a given volume? In a concentrated solution, you have more of solute in a given volume. All right, in a dilute solution, you have less of the solute in that particular volume, right? So if you don't change the amount of solute, you just increase the concentration, the volume of the solvent or the solution, then the solution becomes more dilute, or what we refer to as less concentrated, right? So we could dilute solutions. You have a relatively small amount of solute relative to the solvent, whereas in concentrated solutions, you have a larger amount of solute relative to the amount of solvent, right? And brackets, those brackets typically are used to indicate the concentration of a solution, right? So now let's consider an example. Consider you're asked to prepare a 1 liter solution of a 1 molar sodium chloride. Well, what does this 1 molar tell us? It tells us that we have 1 moles of sodium chloride per 1 liter of solution, right? It's moles per liter. Okay, so 1 molar is equal to 1 moles per liter of sodium chloride. Well, if we are really wanting to prepare a solution, what we need to know is how many grams of sodium chloride do we need to weigh out, right? Well, we could set it up. If we know we have 1 mole of sodium chloride per 1 liter of solution, right? That's molarity, moles per liter. All right. But then what's the volume of the solution that we wish to prepare? 1 liter. So we can multiply that by the volume of solution we wish to prepare. Okay. And then if we want to actually prepare it, we need to know how many grams of sodium chloride do we need to weigh out. So how can we convert the moles of sodium chloride into grams, right? Molecular weight, right? Anytime you need to convert between grams and moles or moles and grams, remember the molecular weight gives you the moles per, or the grams per moles, right? So we could multiply that by 58.44. That is the molecular weight of sodium chloride. How did we determine the molecular weight of sodium chloride? Well, sodium is in group 1A in period 3 of the periodic table, and it has an atomic weight of 22.990. Remember, it has units of atomic mass units, right? Which is equivalent to grams per mole, right? What else do we have? We have 1 chlorine, right? And chlorine is in group 7A, and it's also in period 3 and has a molecular weight or an atomic weight of 35.453. 35.453. Again, it has units of atomic mass unit, but we're looking at its molecular weight. And if you add those up and you round, you should get 58.44, all right? So you won't always be told, or you typically won't be told, that you need to figure out the molecular weights. Okay, that is something that you'll start thinking about anytime you need to convert between moles and grams or vice versa, right? So we'll multiply by the molecular weight. And if we do so, we'll get the mass of, or the weight of sodium chloride that we need. Okay, so we're going to multiply. Well, molecular weight, think of it as a ratio. We could say that we have 1 mole of sodium chloride per 58.44 grams of sodium chloride. Or we could have it as the opposite. We could have 58.44 grams over 1 mole, right? But always think of what do you need your final answer in, and how do you need your units to be canceling out, right? And because of that, we will say that for every 1 mole of sodium chloride, we have 58.44 grams of sodium chloride. Right? So liters of solution cancels out with liters of solution. Moles of NaCl cancels out moles of NaCl. Right? So you end up with 58.44 grams of sodium chloride. Now we need to prepare it a 1 liter solution. So it means what we would typically do is go to the balance and weigh out 58.44 grams of sodium chloride, right? And then we'll basically use a volumetric flask, and they're typically marked. So this would be like a 1000 milliliter volumetric flask, and we'd add water, which is our solvent, to the mark, which indicates 1000 milliliters, and we would mix the solution. And we would say that we have a 1 molar sodium chloride solution, right? So 1 M is 1 moles per liter, which is what we say when we're actually saying it, we say 1 molar solution, right? So molar is basically the capital M, which is basically the unit for molarity, right? 1 molar or 1 moles per liter, right? That's how we were describing molarity. Or the concentration of the solution. All right, so we could prepare a less concentrated solution from what we call a stock solution. A stock solution is basically the more concentrated solution. We could dilute it by adding more solvent, right? We're really not changing the amount of solutes. The amount of solutes are the same. We're just adding more volume of solution or of the solvent, right? So the solution becomes dilute, right? So how can we determine how much of the concentrated solution do we need? What's the final volume of the solution, the diluted solution? Well, we are going to use an equation, right? That will hopefully make sense. Consider you wish to dilute a 12 molar hydrochloric acid solution into a 1 molar solution, right? Again, capital M is molarity, which has units of moles of solute per liters of solution, but when we're actually saying it, we say molar. So we would say a 12 molar solution, right? In case the terms. All right, so consider you wish to dilute a 12 molar hydrochloric acid solution into a 1 molar solution. Which one is more concentrated, 12 molar or 1 molar? Yeah, this one is more concentrated. All right, think of it that you have 12 moles of hydrochloric acid in 1 liter of solution, whereas in this case, you only have 1 moles of hydrochloric acid in 1 liter of solution. So you have more solutes in the 12 molar solution. Okay, so we ask ourselves, how much volume of the stock solution do we need to use if we're not told? And we also ask, how much volume of the diluted solution do we need to prepare? Right, so we use a very useful formula really. M1V1 equals M2V2. Now that's one that you should know, not one that's given to you, right? Where M is molarity, all right, which is moles of solute per liter of solution. Volume is the volume of the solution, all right? M1V1, think of it as the initial molarity times the initial volume equals the final molarity times the final volume, or M1V1 equals M2V2. And you're typically solving for one variable, right? So molarity of the initial stock solution, molarity of the final solution, the desired volume of the final solution, and the necessary volume of the stock solution, all right? So if it's typically less than what we needed initially, all right? So we say we're diluting it by a specific volume. So we're using less of the initial solution, right? We won't be using the entire solution, just a small amount, and adding more of the solvent. So let's take a look. Okay, so we have a 12 molar hydrochloric acid solution times V1. We don't know what the volume is. And we also know we have a 1 molar hydrochloric acid solution times V2, right? We don't know. We weren't really told in this case any of the volumes. So we have to decide, right? We have to decide either the initial volume, or we have to decide on the final volume if we're not told. You must decide how much we need to prepare. Right? Typically, you'd be told the actual volume. So suppose we actually wish to prepare 100 milliliters, right? And then we could solve for it. We could simply rearrange. Our only unknown is really V1, right? So M1 V1 is equal to M2 V2. If we divide both sides by V1, then M1 cancels M1, right? V1 cancels V1, and we're left with, that's not what we're trying to cancel out, right? We're trying to solve for V1. So we're going to divide by M1, right? M1 cancels M1, and then we get V1 is equal to M2 V2 over M1. Okay, we divided both sides by M1. So we could solve for it. Okay. So then V1 is equal to 1 molar of hydrochloric acid times 100 milliliter over 12 molar hydrochloric acid. And if we calculate it, we'd get exactly 8.33 milliliter. What does that mean? It means we will take 8.33 milliliters, okay, of the 12 molar hydrochloric acid solution, right? And then we will add the difference in water up to, or until we reach 100 milliliter, right? So if you wanted to figure out the amount of solvent you need to add, then you're going to take 100 and you're going to subtract that by the amount that you need from the initial stock solution. So we would end up adding 91.7 milliliter of solvents, right? So if we have a volumetric flask, for instance, we're going to put 8.33 milliliter of a 12 molar hydrochloric acid, and then the rest is going to be water up to 100 milliliter, right? So just keep that in mind. What are we solving for? What is the question asking us? All right, so now we're going to work out some problems. Consider you wish to prepare a 3 liter of a 0.5 molar calcium chloride solution from a 10 molar stock solution. What do we need? So suppose you wish to prepare a 3 liter solution of a 0.5 molar calcium chloride, right? And it's giving you what the stock solution is. Right? So what type of problem does it look like? Does it look like we're calculating the molarity? No, it appears to be more like a dilution problem, right? Where you're actually given that this is the final volume that we need, or V2, and our desired molarity that we need is 0.500 molar. That's our final molarity that we're looking for. And we're starting with a 10 molar stock solution. Okay, so 10 molar stock solution. So if we think of the equation, M1 V1 equals M2 V2, what variable are we solving for? Yeah, we're solving for the initial volume. How many liters or milliliter, what volume of the initial stock solution do we need to prepare a 3 liter of a 0.1 molar or of a 0.5 molar solution? So we could rearrange, right? V1 is equal to M2 over V2 divided by M1, right? So if you do the calculation, you really have the final volume times the final molarity divided by the initial molarity, right? That would give us the volume that we need, right? Notice molarity cancels out molarity. We're going to end up with the volume. So 3 times 0.5 divided by 10. What do you get? We'd get 0.15 liters. Right, so we would get that V1 is equal to 0.15 liters, right? That's 0.15 liters of what? That's 0.15 liters of the 10 molar solution, right? So then how do we prepare it? Well, let's take a look. Our final volume is 3 liters, and we will only use 0.15 liters of the 10 molar solution. So the way we would prepare it is we'd use 0.15 liter of the 10 molar solution plus 2.85 liters of, if we're just using water as a solvent, we'd use 0.85 liters of water, which is basically, in this case, our solvents, right? Notice what and that's the 2.85 is simply 3 minus 0.15, right? So let's analyze the answers. The 0.15 is not water, it's the volume of the initial of the stock concentration, not of water. 0.15 of the 0.5. Well, we're trying to prepare the 0.5, right? And we're trying to prepare 3 milliliters of the 0.5. 2.85 liters of the 10 molar. No, 2.5, the volume that we need of the 10 molar is what we were calculating for, and it's not 2.85, right? So in this case, D would be the correct answer. Okay, so we would measure 0.15 liters of the 10 molar stock solution. I want to erase, all right? We'd add it in a volumetric flask, and if we wish to dilute it to 3 liters or 3,000 milliliters, suppose we have a volumetric flask that is marked exactly to 3 liters, then we would add the remaining of water, or 2.85 liters of water. We would end up having a less concentrated solution, a 0.5 molar instead of a 10 molar solution. Did the number of moles of calcium chloride change? No, the number of moles of calcium chloride is still the same. The amount of solute is still the same. The volume of solution is different. And that's when we're diluting something, right? From a more concentrated to less concentrated. Okay, so now let's consider a different problem. What's the concentration? Now it's asking us for concentration, right? And at the moment, the only unit for concentration that we looked at is molarity, which has the symbol capital M, which has units of moles per liter. Okay, so what is the concentration of the solution when 29.22 grams of sodium chloride is dissolved in 500 milliliters of water? Can we identify the solute in the solvent? Yeah. The sodium chloride is dissolved. The sodium chloride is dissolved in something. It's dissolved in water. So water is our solvent, right? And sodium chloride is our solute, right? And what we have is moles of solute over liters of solution. Well, molarity is moles per liter, but what we're given is actually the mass of the solute. How can we convert the mass of solute? How can we convert the mass into moles? What do we need? What do we need to convert the mass into moles? Yeah, exactly. We would need the molecular weight, which has units of grams per mole. All right, so let's take a look then. Sodium is in group 1A in the periodic table. So we're actually going to start by calculating it. I'm going to calculate the molecular weight of sodium chloride. We have 1 sodium per 1 chlorine. Sodium is 22.990 grams per mole. Chlorine is 35.453 . Again, grams per mole. And if we add it up, we just did it a little bit ago, 58.44, right? We're going to get 58.44 grams per mole of sodium chloride. Again, anytime you need to calculate the molecular weight, you won't be told, all right? That's something you would have to figure out based on the fact that you are trying to go from mass into moles or moles into mass in grams, right? So we have 58.44. Okay, so that's the molecular weight. Again, we could say grams per mole or mole per gram. Okay, so let's try. We have 29.22 grams of sodium chloride. And we know that for every mole, we have 58.44 grams. So for every mole, notice our final unit of concentration is moles per liter, right? So we want moles on top, right? And we also need grams to cancel out. 58.44 grams. All right, and then again, that's sodium chloride. That's sodium chloride. Okay, what do we get if we take a look at the units? Grams is canceling out grams, right? Well, we're left with moles, but what we need is concentration. We need our final answer in concentration in moles per liter, right? Well, we know we have 500 milliliters of water, right? That's 500 milliliters. To convert that into liters, you could multiply. We know that 1 liter is 1,000 milliliters. So it's like moving the decimal place 3 units to the right, right? 1, 2, 3. So 500 milliliter is really equivalent to 0.500 liters, right? So I'm just going to go ahead and use liters, but that's and something important. If you're given the volume in milliliters, just remember to convert that into liters because molarity is moles per liter. So we're going to multiply that by 1 over 0.5000 liters. Why, divide, not multiply? Again, I always say, keep track of the units. Ultimately, the units are going to cancel out. The units are going to cancel out and you will end up with the unit of interest. In this case, moles of solute per liter of solution. Okay, so we have 29.22 times 1 mole over 58.44 grams times 1 over 0.5. It gives us 1 molar or 1 moles per liter, right? So D would have been the correct answer. Now let's take one more problem that kind of covers the concept when we talked about Avogadro's number or the number of molecules. Remember, 1 mole is equivalent to Avogadro's number of molecules. So if you're given a problem and you're asked how many molecules, just remember that correlation, right? That 1 mole is going to equal 6.022 times 10 to the 23rd molecules. Okay, so how many molecules of sucrose, and they gave us the molecular formula of sucrose as well as its molecular weight, right? So we're given the molecular formula and we're given the molecular weight, are contained or are present in 14.3 milliliter of a 0.14 molar solution of sucrose. Well, if we ultimately are looking for the number of molecules, then what we also need to keep in mind is that we'll need to know how many moles we have, right? So how can we go from volume and concentration into moles? And do we need to use the molecular weights? Okay, let's start with what we're given. We know that 0.140 is really molarity, which is moles per liter. And ultimately, to get into moles, we need to calculate the number of moles that are present. Okay, so we will say we could start with volume or molarity. I just have molarity right here. So moles of sucrose per 1 liter of solution. Right? But what volume of solution are we using? 14.3 milliliter. And again, just divide by 1,000 to get into liters. So we are multiplying it by, and I just need to cancel the volume. So I'm just going to multiply by 0.012. So removing the decimal place. 1, 2, 3. 0.0143 liters. Again, to convert into milliliters, think of it, you're multiplying by 1,000. 1, 2, 3. Right? So 0.0143 liters of solution. Right? This would give us the number of moles. Right? Liter of solution cancels out liters of solution. We would end up with moles, but we're really interested in the number of molecules. Well, we know that, notice we need to cancel out moles and we're interested in molecules. We know that 6.022 times 10 to the 23rd molecules is equivalent to 1 mole, right? So then moles would cancel out with moles and we end up with molecules, all right? 6.022. So if you do the math, I believe you'll get 1.21 times 10 to the 21st molecules of sucrose. Okay. So let's take a look at the next problem. Let's see. Determine the molarity of a solution formed by dissolving 468 milligrams of magnesium iodide in enough water to yield a 50 milliliter solution. Okay, so let's look at what we are looking for. We're looking for the molarity, right? And it was formed by dissolving, right? We're dissolving it in water. We're dissolving something in water, right? So water is our solvent, right? Which really also indicates that magnesium iodide is our solute, right? And we know that molarity is moles per liter, moles of solutes per liter of solution. And also something to keep in mind is the units. You're given the units in milligrams, right? Okay, so how can we convert? So if you think about it, we ultimately need molarity. Molarity is in moles per liter, all right? how can we convert, but we're given mass and volume. So how can we convert the mass of the solute into moles of solute? Yeah, using the molecular weight, right? So we have 0.468 grams of magnesium iodide. Again, I converted milligram into gram by dividing by 1,000. Milli is 10 to the -3. So that's grams, but ultimately I need moles. So I need to calculate the molecular weight of magnesium iodide, right? So magnesium, how many? I have 2 iodine per 1 magnesium. So I'm going to take a look at the molecular weight of iodine, or the atomic weight of iodine in the periodic table. It's 126.9. But I have 2, so I need to multiply it by 2. And for magnesium, I only have 1. And if I take a look at it on the periodic table, it's 24.305. Right, and then what you'll do is you'll add those values up. You should get 278.105, and that's the unit in grams per mole, right? So we can multiply by 1 mole over 278 grams, or 278 grams per 1 mole, but ultimately we need our unit in moles per milliliter. So we'll do 1 mole of magnesium iodide over 278.15 grams of magnesium iodide. Okay, so now what we're left with is really the number of moles, correct? Okay, so if we take a look at our units, grams of magnesium iodide is canceling out with grams of magnesium iodide, and we're left with the moles, and our molarity is in moles per liter, right? So we need to divide by the volume. So times 1 over, we have 50 milliliter, or 0.050 liters of solution, right? So in your calculator, you can do it as a single calculation, just open parentheses, 0.468 times, in this case, just 1 times just 1. You could ignore the ones since they're 1, just showing you in case it's something else. And then divide by, open parentheses, 278.105 times 0.050. Right? And if you do it correctly, I believe it's 0.0337. Right, let's do double check. Let's actually calculate it. 278.15. Yeah, you'd get 0.0337. All right, I hope this was helpful, and I will see you all next time.